For our presentation, we selected our topic as the application of linear algebra in electrical circuitry. In the following slides, we will introduce the key components of a circuit, how they can be represented and analyzed using matrices, and we will talk about some of the real-world cases for when these methods would be applied to solve problems regarding electrical circuits. To begin, you may be wondering what an electric circuit is. An electric circuit is the path that is needed to transmit electric current. Electric current being the flow of charged particles such as electrons or ions. These circuits consist of components such as transistors, capacitors, diodes, and resistors. Ohm's law and Kirchhoff's law are two basic laws regarding electrical circuits that we will talk about later in this presentation. The key components of a circuit needed to solve matrices include the battery, the wires, resistors, and the direction of current. The battery provides the voltage necessary for current to flow through the circuit. It is the power source of the circuit, and its positive and negative terminals determine the direction of current. The wires are the conductors that allow the electricity to flow between components. They provide the necessary connections between components in a circuit. Usually, the material and diameter of the wire can affect the circuit's efficiency and resistance. The resistors control the flow of current in the circuit by adding resistance. They protect other components from excessive current, causing the circuit to short. The resistance is measured in ohms, which will be seen in the math portion of this presentation, and different resistors have different resistance values. The direction of current describes the orientation of the battery, as mentioned before. When the current flows from the positive end of the battery, the circuit is in a positive configuration, but when the current flows from the negative end, the current is in a negative configuration. The direction is usually denoted by an arrow as seen in the diagram.
Following on what Dean said, we are going to look at the background of the problem. Electrical circuits are used everywhere today to transfer electrical current to other forms of energy. Examples range from many things, but the two I believe that you will find common are the lights in your house to even the fridge in your house. The example covered later in this presentation is going to be a complex circuit with multiple resistors, two batteries, and current messages. We use the formula Ri equals V to solve for the current of 4 loops. We're going to look at the diagram and we're going to gather 4 linear equations from the diagram. And with those 4 linear equations, we are going to transform it into a matrix. And we are going to use linear algebra to solve for the current I. Why is the problem important? The problem is important because current is needed to know whenever dealing with circuits or even electricity, of course. Using matrices to solve for the current gives the essential information needed to the workers who need the information to build on it more. Examples like this are going to be companies like TECO and other electricity companies all around the world. They need to know the amount of current that's flowing throughout the neighborhoods and cities and many more.
So what kinds of linear algebra techniques can we use to describe the properties of circuits? We can use matrices, we can use matrix equations, we can use Gauss-Jordan elimination, and we can use pseudo-inverses. So matrices can be used to calculate the properties of several parts of a circuit all at once. For example, you can find the voltage in every node of the circuit all at once, or you can find the current flowing through every loop or mesh of the circuit all at once, which is what we're going to be doing in this next problem. So our problem is going to be a matrix equation based off of Ohm's law, V equals IR. So we're going to have a 4x4 matrix of resistance values, a 4x1 matrix of mesh current values, and a 4x1 matrix of voltage values. So since we're solving for the currents, that's just going to be our variable matrix. The voltages are just going to be the sum of every voltage that's present in that loop of the circuit. So 2 here, 5 here. It's important to note that the 2 and the 5 are facing opposite directions. So they're going to be opposite signs from each other. So we can go ahead and say that that's our voltage matrix. Now for the resistance matrix, for every entry that's on the main diagonal, we're going to add up every resistor. So for loop 1, that's going to be a 4 plus a 2 plus a 2 plus a 1 makes a 9. For every entry that is not on the main diagonal, we look at the resistors that those two loops share. So for spot 1, 2, we look at what loop 1 and 2 share. They share this 2 ohm resistor, so there's going to be a 2 there, except we multiply it by -1. So there's going to be a -2 there, and also here because it's the same no matter what direction you look at it. So this is going to be a symmetric matrix. When all is said and done, we end up with that for our resistance matrix. There's a few ways we could solve this. We could use Gauss-Jordan elimination, or we could use inverse matrices. I chose to use Gauss-Jordan elimination. So most of the way through, you end up with this, just as a little checkpoint, basically. And when you're finally done, you end up with these pleasant-looking values. So that means that in loop 1, we're going to have a current of 3/5 of an amp flowing the opposite direction to what we have indicated here, since that's negative, and similar deal for all the other 3 loops. We can also use matrices to perform more complex operations with more complex circuits. For example, if we wanted to find a matrix A that transforms this matrix I into this matrix capital I, it's a little bit easier said than done, unfortunately. We can try and use left and right inverses. Keep in mind that a given matrix can only have either a left or a right inverse if it's not square and not invertible. But if both the transpose of A times A and A times the transpose of A, if neither of those are invertible, then this matrix will not have a left nor a right inverse. So if we look at our matrix that we're dealing with here that we want to invert, if we multiply by the transpose of itself, we're going to end up with this. And the problem is that every row here is linearly dependent on the first row, because we could, say, divide this by I1 and multiply by I2, ends up with this. So we could make all of these rows zeros, which means that this matrix is going to have a determinant of 0 and therefore is not invertible, so we actually cannot use left and right inverses here. However, any matrix of size Mn can be approximated by a matrix U times a matrix sigma times the transpose of a matrix V, where these matrices are described as U being an m by m matrix of column vectors, which are an orthonormal set of vectors that spans the column space of A. Sigma is an m by n diagonal matrix of the singular values of the transpose of A times A. The singular values are the square roots of the eigenvalues of a transpose of A times A, so it's going to be the singular values and zeros in every other space. And finally, the transpose of V is going to be an n by n matrix that orthogonally diagonalizes the transpose of A times A, which means that when we do the matrix V times the matrix A times the transpose of matrix V, we're going to end up with a diagonal matrix. So now, any matrix A has a pseudo-inverse A plus that's approximated by basically the inverse of this formula, where sigma plus is a diagonal matrix of the reciprocals of the singular values of ATA. So we can use this process to find an inverse to the matrix that we were dealing with on the previous side. However, the problem is that these formulas also include matrix A in it. So we need to know what matrix A is in order to find its pseudo-inverse, which we do not, because it's all just variables. So we would need to plug in some values here in order to be able to actually use the process of singular value decomposition and pseudo-inverses.
Hello everyone, my name is Hayden Burke, and I'm with you today to describe Kirchhoff's circuit laws. Now, Gustav Kirchhoff was a German scientist in the 1800s who helped define 2 laws that solves for an electrical circuit. The first law is the conservation of current. This first law states that the total current entering a junction in a circuit is equal to the total current leaving the junction. So in figure 1, we have a junction right here with an input of 5 volts with some current, and an output equal to the input out of these 2 branches respectively. So both of these branches will contain a part of the input voltage here. Now the voltage law, his second law, states that within a closed circuit or loop, the total voltage is equal to 0. When solving for a circuit, choose a loop in either clockwise or counterclockwise direction, and note of all voltage increases and drops. Now we find the increases and drops by denoting the negative to positive resistors, which will be here in the problems. Those will indicate a negative voltage, and a positive to negative resistor corresponds to a positive voltage. So going from A to B, we have a negative to a positive, that means a negative value. From B to C, we have a positive to a negative value, that gives us a positive value. And from D to A, we have a negative to a positive, that gives us a negative value. Now we put all of these values into an equation, and we equal them to 0, and we solve for the unknown V, and we get negative 4 volts or positive 4 volts if you went to the ADCBA direction. In conclusion, solving for electrical circuits is a critical skill for electrical engineers to have. It is used in the creation of every electronic in use. Without this knowledge, the modern world of communication and technology would be impossible. Linear algebra is an important part of electrical circuitry. Many properties of circuits, such as the current in various loops of the circuit, can be found relatively easily using matrices, matrix equations, Gauss-Jordan elimination, and pseudo-inverses. Utilizing this method of solving for electrical circuits can be helpful in many ways, such as the creation of software that makes electrical engineers' jobs easier, and giving an automated tool to the enthusiasts who seek to create their own circuits and utilize these calculations without schooling. These are our team member contributions, and these are our references. Thank you.